Hi, welcome back to Key Concepts in Technology. This week is the introduction to the week on the Internet. Now, what could be more ready for some major myth busting than the Internet? Everything Internet today seems so obvious, taken for granted, and inevitable. I've been actively using the Internet since 1988, and I've been developing content for the web continuously since 1993. But 15 years ago, I would never have imagined our latest statistics. There will be 3 billion Internet users in the world by the end of 2014. And China leads the world with over 641 million users. Today, there are more than 1 billion websites, over 3 billion daily Google searches, over 4 billion daily views of YouTube videos, and 2.3 billion emails sent every second. We have many kinds of Internet-enabled devices, large and small. And in many countries around the world, the Internet has now become a basic utility like electricity, water, and phone service. The design concepts for the Internet of Things has enabled the ability to use TCP/IP, the Internet protocols, to connect anything in our humanly built environment. And the processes of the natural world combined into an even more vast information system using the Internet. How has all this global internetworking become possible? The readings this week will provide you with a good sense of the technical architecture and the major stages in the history of the Internet, the client-server architecture model, what the TCP/IP protocols do in allowing data to be exchanged, how routers and Internet software work, all the computational and network interactions that happen between your device and the whole system. This description is essential to know, but it doesn't explain the rapid globalization, complexity, and social embeddedness of the Internet today. Well, part of the story of the Internet's success lies in the extensible design principles in the Internet architecture, and the other part in how global networking has to be implemented in the complex fields of social, institutional, and political networks around the world. The network as a system is our mother of all case studies for de-blackboxing complex modular social technical systems and for investigating distributed agency and cumulative combinatorial design. On the tech side, we've benefited from the open architecture of the Internet and the design of TCP/IP, the main protocols for packet-switched data underlying everything on the Internet. This gives us 3 related design principles assumed in the core networking and computing technologies: extensibility, scalability, and interoperability across any physical component. Now, the Internet was designed as an open system so that anyone could build out a physical network and connect to the Internet by following common standards and specific methods for internetworking. But design principles in a technical architecture don't propagate themselves. They have to be enacted. And this leads us, as always, to the complex network that we can't see behind the physical architecture of network devices, wired and wireless connections, data lines, routers, and servers. So, if someone asks you, what is the Internet? Or what does it mean to be connected to the Internet? What does it mean to be on the Internet? Well, you'd probably point to an interface in your mobile device or PC that shows that we're connected. But our individual network connection and local software interfaces aren't the Internet. Now, if we open the black box just a little bit, the first realization is that the Internet isn't a thing, a reified it. Even though we talk about the Internet this way, no, the Internet is something enacted. It's existing for technical mediation of many kinds of activities and functions, a system of many kinds of distributed agency, a network that has to be enacted every day by the participation and cooperation of many kinds of agents, governments, international standards organizations, every country's internal policy and regulation of cross-border communications, and international agreements to make the global connections possible. The large ecosystems of corporations and all the hardware and software manufacturers that have to make things according to strict interoperable specifications. And the list goes on and on. So when we start looking at the internet history, we're going to get lots of surprises. In fact, the internet was born in a perfect storm of historical accidents. There were intersections of development and unforeseen consequences of government and private research, investment, university research, policy regulation. Now, this background may sound really boring, but it gets exciting and interesting really quickly in ways you can use to understand where we are now and possible futures for the internet. The economic and social value of the ideas behind the internet is incalculable. We continue to cash out the stored value in the internet design principles every day. Going back a little, in the 60s and 70s in the US, we saw a convergence of many forces with separate histories, none of which had trajectories that could have anticipated the combinations at all the important moments when the conditions of possibility were in place for forces like telecommunications and computation to converge around digital networks. We had going on simultaneously one technical development in computers and an emerging sense that computers would extend to become information devices for many kinds of users. Two, we had the computer industry that was developed from government and private research, from university research investments. The computer industry was unregulated and free to expand. Unlike my point 3 in convergence, the telecommunications industry, on the other hand, was highly regulated, but with one major exception: leased data lines. Telecom companies and businesses could develop and install private leased lines for data communications. No regulation like telecommunications for voice. And the fourth component, the government-funded initiative through DARPA for a new data network. You'll read about this in the background readings this week. Well, in the late 60s and early 70s, the packet switching concept being developed by ARPANET, which was a project funded by the government and university labs, developed the first concept for connecting computers using leased data lines through this loophole in regulation. The ARPANET project had two huge engineering problems to solve. How do you enable mutually incompatible computers to communicate and exchange data across a network? And how do you design a computer network with no single point of failure that could bring down the whole network? Now, the packet switching concept solved this problem, and it actually worked. The final specification for implementing these concepts in the architecture that we now call the internet was developed by Vint Cerf and Robert Kahn in the mid-1970s in the TCP/IP protocol suite. That's Transmission Control Protocol for managing the flow of data, and Internet Protocol for managing computer addresses so that they can connect together. At the same time the ARPANET project was going on, we had emerging developments in information digitization and digital media. People working on computer design saw that any symbolic system, text, images, sounds, math, could be digitized and represented in sets of bytes that a user could process. And deeper in the concurrent dependency stack are developments in electronics, computer screens, processors, computer components, operating systems. Each of these with their own histories of development with no built-in inevitable convergence. In the 1980s, universities and government agencies continued developing what we could do over TCP/IP, including email, the first killer app, the first digital libraries, and systems for file sharing. The other major happy accident was the timing of internet development and the convergence with the PC industry. When the US government opened the internet to commercial and consumer use in 1994, the PC industry had already developed many kinds of computers using graphical interfaces and a growing home and office market. PCs were at first retrofitted to be able to connect to a data network over telephone lines, and now, of course, network chips for wired and wireless data connections are standard equipment. Who could imagine a PC or a computer device without a network connection? But there was no inevitability in the convergence of PCs and networks. Timing can be everything. The rest, they say, is our history. So the internet isn't a thing or an external object that can have effects on us. The internet is a social, technical, political, and economic system enacted through the participation of multiple agents in one of our most complex orchestrated combinations of prior combinations, in Brian Arthur's terms. Understanding the key design principles of the internet and how they get implemented on the ground in all our real-world social and political contexts is knowledge you can use every day. Knowing what's behind the architecture will enable you to participate in big issues or design new applications. Recently, we've had a major debate about net neutrality among corporations who own network infrastructure, like AT&T, Verizon, and dozens that you've probably never heard of, and those who own access to content and media services and entertainment. And often, these owners are the same, who own the architecture and the content. And we have legacy policies in the FCC trying to figure it all out. So the big open question is, how can we reorchestrate regulatory policy and the political economy regimes for media, data, entertainment, and communications after all this convergence on the common platform of the internet? Internationally, we also have major complex debates involving all the actors around how the extensibility and scalability of the internet will be managed, how to provide access, who pays, who controls information, how do we manage privacy and security in a system designed for openness. The more you uncover what's in the black box, the more you can participate as part of the future of the internet.